Okay, now, you know that we have said that Newton was able to compute his laws of motion because he was able to invent calculus, okay? The differential and the integral calculus. And the central idea in calculus is to try to approximate curves by linear line segments, as we have said before. And that's actually the entire idea of calculus, as you can also read from the Baranger article. This is the fundamental insight of calculus. And of course, if you are going to represent a curve by a line segment, then the curve has to be smooth. And another way of saying that a curve is smooth is to say that the curve is represented by a function which is analytic. So analysis and analyticality, etc., come from the requirement that you can divide a complicated shape like a curve into simpler pieces like line segments. It's also true for surfaces. Surfaces can be, if the surfaces are smooth, again, you can approximate the surface by tangent planes, small tangent planes. These are the fundamental concepts in calculus. So the idea of analysis, which is to try to understand, which is something big and difficult to understand, by trying to put it into pieces, divide it into pieces which are easier to understand, is common both to the idea of analysis and also to calculus itself. Associated with this, of course, there's the idea of reduction. You reduce reduction and analysis. What's the difference between these two? Well, essentially they are the same thing, but when we use the reduction, we sometimes imply that we reduce to the limit, to the level of particles if it is something physical that you are analyzing. Now, the Newtonian paradigm, therefore, which came to be known like this, the understanding. You remember the paradigm is a Weltanschauung or worldview shared by a group of people. So the group of people here are the scientists. The scientists share mostly the Newtonian paradigm, which says that objective knowledge is possible, and the possibility of objective knowledge depends on the assumption of subject-object duality, as you know. Cause and effect act linearly. Non-linearities are not considered in most cases. This is called the superposition principle. For example, in electrical engineering, the fundamental graduate course when I was a student there was linear systems, the course on linear systems. And the idea of entire electrical engineering education is that superposition is possible. Superposition means that when several signals are acting one by one on a system, the output can be computed by superposing, that is adding the effect of each individual stimulus. That's again linearity. Of course, there are nonlinear systems as well, but in linear systems, this is what they do. Most engineering works like this. That nature is deterministic, and if it's not deterministic, even if it is probabilistic, then the distributions are known. The probability distributions are known, which we can use to make predictions. It's predictable. And reduction works. Now, Newtonian science has been a huge success. Well, we owe everything to Newtonian science, the technical systems that make life easier for us, or even though it makes it complicated, are a result of the technological society, is a result of Newtonian science. It dominates, this view dominates our everyday view of the world even today. Now let's go over to complexity. As I have explained before, and these articles show, that in the 20th century, two things happened in the 20th century in physics. The relativity and the quantum theories were proposed at the beginning of the 20th century. Quantum mechanics, when it was developed sufficiently, was seen to was or indicated that the laws of motion, the laws of mechanics as they were formulated by Newton, did not work in this case of particles, subatomic particles in quantum mechanics. Newtonian's law didn't apply here. In biology, for example, analysis and reduction was seen to be not to work. You could not understand living organisms by cutting them into pieces. You had to observe the living organisms in its environment, in its habitat. Like other sciences like meteorology, climatology, etc., so that nature was more complex than we thought, and it couldn't be understood easily using a calculus way of thinking, using analysis only. There's also the principle of uncertainty that was demonstrated by Heisenberg, who showed that the two attributes of a particle like momentum and mass could not be determined at the same time. If you try to measure the mass of an electron, for example, it becomes impossible to determine its momentum, its speed. If you try to measure the speed accurately, then it becomes impossible to measure the mass, which means that the observation of the object, of the electron, actually affects the electron, and subject-object duality does not work in these cases. So insufficiency of analytical thinking gradually came to be apparent in the sciences. The failure of calculus, for example, in studying complex shapes was evident. So realization that nature is more complex than previously thought it was led to the development of a new area of studies which we now collectively call complexity studies. These are studies where calculus does not work, where systems are nonlinear, where reduction doesn't work, where laws of motion of Newton fail. Complexity theory is as yet not fully developed. We cannot speak of a complexity theory. There is no such recognized theory as yet. It's a new area. Its aim is to discover unified laws governing complex systems through interdisciplinary research. Interdisciplinary inquiry is essential in complexity studies. So this is another way which separates it from Newtonian science. In Newtonian science, we conduct disciplinary studies usually in one discipline. It's yet early to say whether the aims of complexity will be realized. Now, a concept which is related to complexity is the concept of chaos, and the Barangé article makes a very good job of explaining what chaos and complexity are. So let's go through these. Chaos is associated with systems that are subject to nonlinear dynamics, where linearity and superposition does not work. Any system that is subject to nonlinear dynamics will be chaotic, as we shall see, in some region of its phase space. Now, the concept of phase space is, again, a very, very fundamental engineering concept. It is related to the concept of state space we already talked about. But this is more general. A phase space in physics, for example, is defined. Let us take the example of a container full of some gas, a container full of carbon dioxide or air molecules or whatever. This is a system now. What would be the phase space of this system? The phase space would consist of the spatial coordinates of each particle of gas, of each molecule of gas, the XYZ coordinates in space, plus the momentum, the motion of the particle. And the motion you have do they still teach you dynamics? Statics and dynamics, do you take course? Well, if you have taken the dynamics course, maybe you haven't. In the dynamics course, for example, vector motion is studied. For example, an aircraft flying has its momentum, also has 3 coordinates. Vectorial motion is can be divided into coordinate motions in 3 coordinates. So 3 coordinates for location and 3 pieces of information for location, the x, y, z coordinates, and 3 pieces of information for the momentum. If all these are known, suppose there are n particles in the container, n gas particles, okay? 6 times n dimensions make up the phase space. Okay? The phase space, therefore, is the space. Any point in the phase space gives us information about these 6 entities, the space coordinates and the motion coordinates. This is what we mean by a phase space. Now, I talked about the 2-body and the 3-body problems probably before when we mentioned Newton for the first time. Newton's laws of motion, for example, for the 2-body problem, end up with a very simple formula of an ellipse, for example, which determines the orbit of the Earth around the Sun or the orbit of the Moon around the Earth. That's the 2-body problem. And it can be solved analytically. We have a formula. This is also solved as an exercise in calculus books sometimes. And then using that formula, you can determine the location of the Earth or the Moon around the Earth at any future time. It gives you complete information. When Newton tried to develop similar results in the case of 3 bodies, he was not able to do that. But he thought that somebody would come up and would be able to solve the problem later on. And for about 200 years, mathematicians worked on this problem without success, finding a closed form solution to this until the French mathematician Poincaré, as I have told you, proved that an analytical solution was impossible for the 3-body problem. In fact, of course, we could calculate the relative positions of the 3 bodies rotating around each other by using numerical methods. Numerical analysis, approximation calculations using because computers provide this possibility. Before we had computers, it was impossible. But computers, since they can calculate many operations in very small duration, it's possible to solve the 3-body problem approximately. But it was discovered that you see, if the initial conditions are known, then you will be able to determine the positions of the 3 bodies at time t, where t could be 2 months from now. But using even the computer calculations, the initial conditions, that is, the initial positions and the initial position in the phase space, instead of n gas molecules, now we have 3 bodies. The phase space of these 3 bodies will consist of the spatial coordinates and the momentum coordinates of the bodies. If these are known at time t0, for example, using a computer, you could compute them at time t. But how do you know the positions at time t0? Well, we know them, but how do we record them? You have to record them in the memory of the computer. Computer memory is finite. How many decimal points will you take after how many decimal places will you take after the decimal point? The computer memory, the precision of these variables is finite. And even if you carry 20 decimal places after the decimal point, then the 21st decimal place could make a difference. And if you use a very powerful computer with a very long word length compared to a computer with a shorter word length, for example, the solutions computed for time t were completely different. a very small difference at the initial conditions produced a huge difference at the final solution. So this is known as STIC is an acronym that's used, sensitivity to initial conditions. This is what we mean chaos in time. Some systems, some nonlinear systems obeying nonlinear dynamics have this sort of behavior, meaning that their position in phase space at any time t in the future is subject to extremely sensitive to the initial conditions. And since the initial conditions cannot be represented exactly, no measure is exact, it is impossible to predict the motion of such systems into the future properly. So this is what we mean by chaos in time. Chaotic systems are systems that in some regions of their phase space actually are chaotic, or most nonlinear systems, let us say, are chaotic at least in some region of their phase space. And this leads to unpredictability. This is known as the butterfly effect in popular language. Examples, well, I have written this wrong. I mean, these examples of glasses, mountains, earthquakes, etc., are not examples of chaos in time, but chaos in space. We shall come to that in a moment. Now, predictability is not entirely impossible. In chaotic systems, sometimes making predictions is possible. The region of the phase space where some sort of predictions can be made is called edge of chaos. Have you heard of this term? In scientific literature, in popular scientific literature, this is something you hear all the time, edge of chaos. Living organisms live at the edge of chaos. What does it mean? For example, let us take the climate. The butterfly effect actually was an example when the climate was under investigation. If this butterfly flapped its wing in some way, then it would make a difference in the weather in Europe 2 months later, because the butterfly flapping its wings in this way or in that way will make a difference in the initial conditions. It will make a very small difference after the 30th decimal place after the decimal point, but it will still make a difference. So that's what we mean by saying that the weather cannot be predicted. In the Amazon, for example, the weather forecasts are made only 5 days into the future. If you go on the internet and look for weather forecasts, they always give you 5 days forecast. After 5 days, it becomes chaotic. Nobody knows what the weather is going to be like. But we know some things. For example, we know that the Amazon River will not freeze. It will not snow in the Amazon. The Nile River, for example, never freezes. It's never frozen. So there is chaos, but there is some regularity. This state of reverting, this state of, it's not a steady state, but this state that the system goes back time and time again is called a strange attractor. An attractor is a stable state. Not stable in the sense of Newton. If a state in the phase space is stable in the Newtonian sense, when the system enters that state and you give it a small perturbation, you move it a little bit away, it comes back to that state all the time. It's like a ball, for example. You take a ball, you put a ball in it, it sits at the center. If you move it again, it comes back to the center because of the center of gravity pull. So that's stability. So what's the opposite of that? It can be unstable. Where the system will visit is completely unpredictable. So there are these two extremes: stable behavior, deterministic systems have stable behavior, and unstable behavior. Chaos is in between these. In chaos, there are some states between instability and stability, which we call strange attractors. These states are visited often. Chaos in space also occurs, and the concept for chaos in space is the concept of a fractal. A fractal is mountains, earthquakes. Well, earthquakes are also chaos in time. I should have corrected these examples anyway. A human body is a fractal, for example. What do you mean by a fractal? A fractal is an object which does not become simple when you divide it into parts, which is not analyzable. A human body cannot become simple if you divide it into parts. Some of these fractals are self-similar. When you divide them into parts, they retain all the properties that they had before division. So the example of a glass, for example, think of the glass in front of the car, automobile, the windshield. When you are driving fast, sometimes something happens, a pebble is thrown at the car from the wheel of the car in front, and there's a crack in the window. It's a small crack. So after some time passes, the crack extends, it moves. This is chaotic behavior. Nobody can predict where the crack is going to go. All right? Another example is sand hills. Let us assume that you are in the seashore. You take sand and you let the sand grains drop one by one. What happens is that the sand grains will accumulate in the shape of a conical hill. Right? You keep doing that. You drop the grains exactly at the top of the cone. But after a while, suddenly the heap will give way, and some of the sand will flow away. That's also chaotic. Chaos can be obtained, can be observed in all these. It's unpredictable how that will occur. What sort of a shape, in what sort of a shape will the hill collapse? So these are all examples of chaos in time and chaos in space. The conclusion is that all nonlinear systems are chaotic in some region of their phase space. Hence, complexity implies chaos, but chaos can also occur in simple systems. Okay? When you have complexity, we did not define complexity yet, but complexity implies chaos. So we have chaos. Let's stop here.